All right, so very quickly, take about 30 seconds to 45 seconds to do example 7A on your own, and we'll do it together shortly thereafter. It may take you a smidgen longer than 30 seconds. At least you'll have a plan of attack by then. It says, watch out for indeterminate forms when you're evaluating. Hopital's rule can kind of be a tool in this section when you're evaluating. Feel free to do them MC style if you want, without the limit in front. It's fine. If you feel you need to practice it, because on a free response you're not going to be able to pull it off, then practice what you need to practice. Maybe, yeah, the virgin pina colada. Good. I see some of y'all integrating this the right way. There's a couple of things that you could do with that e to the negative x. You could bring it to the bottom. It would make it e to the positive x, but would it help you find the antiderivative? Maybe not. Maybe so. Let's explore that. 1 minus x over e to the negative x. Yeah, that doesn't really help. Yeah, but see, we're not trying to evaluate the limit. We're trying to evaluate the integral. So Hopital's rule doesn't work until we're ready to evaluate it. This doesn't help us find the antiderivative. So what we have to do instead is distribute. Or put it over x and then split it up if you want. But in this case, it's already ready to distribute. So you get e to the negative x, and you get minus x e to the negative x. And remember that if you have more than one term in your integrand, you need parentheses around it. Now, the first term is pretty easy to integrate, right? It's just an e to the negative x with the correction of a negative 1. The second term is going to require, let's see, let's just go off to the side, do some bench work here. If I were just faced with that. Yeah, integration by parts. Yeah, integration by parts. Very good. So this one is going to work with the single method, but if you want to do the tabular method, that's fine. U dv plus minus. So u would be what? What would we prefer to choose u to be? X. Its derivative is 1, and then we hit 0. And we got e to the negative x. We're going to have a correction of a negative each time. It becomes positive. And then plus, minus, plus. So here, if we exhaust our resources, we'll have the first diagonal. We get negative x e to the negative x. Go ahead and pick up the next sign, minus. The next diagonal is actually going to be a positive, so we keep the minus in front. E to the negative x, go across, and then it'll be plus what? C, for the antiderivative. Now, if we need to use that over here on the second term, we can import that. So the antiderivative e to the negative x is negative e to the negative x. And notice this negative right there, I did not include that in my chart over there. So when I bring this back in, I'm going to have to distribute the negative, which effectively changes both of the signs. So it'll become a plus x e to the negative x and a plus e to the negative x, distributing. And I don't want the plus c because it's a definite integral. And again, we're doing it MC style, so 1 to infinity. But simplifying, hey, simplifying. Those cancel. That's pretty good. So we're just left with x e to the negative x. Now here's the cool thing. At this point, you're not going to lose any checks because you haven't evaluated yet. So if you want to hold off on writing the limit, if you wanted to use the limit, until this step right here, this would be kind of the latest in the game you can introduce the idea of the limit. Because after this, you're really evaluating. And that would still be okay. Because as long as the evaluation comes from a limiting process, you'll get that check. So I'll go ahead and do it with the limit now since I wrote it. So I get b e to the negative b. Now, if you want, you could go, that's the same as b over e to the positive b, for those of you who took e to the negative x to the bottom, you could still do that, b over e to the b, and then minus, plug in a 1, you get 1 over e to the 1th, which is 1 over e. And now it's time to take the limit as b goes to infinity. Well, you're going to plug in the top and you're going to get infinity, and you're going to plug in the bottom and you get infinity. So if you needed to, you could use L'Hopital's rule now because you have infinity over infinity. Up here you would have had infinity times 0, which would have been a multiplicative version. But do we really need L'Hopital's rule for this one? It wouldn't be bad. The derivative would be 1 over e to the b. But you can also do it by growth rates because we're approaching infinity. So exponentials grow a lot faster than linear. So the first term goes to 0. Yeah. We get the limit as b goes to infinity. Oh, we already evaluated. Sorry. We get the answer to be 0 minus 1 over e, which is in fact just negative 1 over e, or negative e to the negative first. Is it okay to have a negative number? Sure. Yeah. The integral can be negative. We didn't set it up ourselves finding a volume or an area, so it shouldn't be too alarming necessarily to get a negative number. So distributing there worked. All right. This one here, e to the negative x sine of x, the integral from 0 to infinity. How are we going to find the antiderivative of that? You have a factor that's e to the x, so you can take its derivative or integral, and you have sine of x, which you could also take its derivative or its integral. This is another one of those by parts. And this is one that I told you back in the day you probably would not have on the AP exam, but you might have in here. In fact, we do have it in here. Neither one of these things are going to expire to 0. They're just going to keep rotating. So this is the one where you're going to try and tie it off when you get those two factors again, and then you'll group everything on one side. So if you forgot how to do that, I'll show you how to do it. Again, u dv plus minus. So tabular method. It doesn't really matter which one we call u and which one we call dv. So you tell me. More people mess up on the antiderivative of the trig functions. So with that in mind, I would suggest maybe letting u be sine and dv being e to the negative x. But it really doesn't matter as long as you're doing it correctly. So the derivative of sine is cosine. The derivative of cosine is negative sine. Derivative of negative sine is negative cosine. When do I stop? I don't know. I'll stop there and do more if I need to. And then each time here, we're just going to have a negative correction. So kind of like before. And I'll just put a few terms down and get more if I need it. So we're always going to take the first diagonal, which in this case is negative e to the negative x, sine of x. We pick up the next term is minus. Now, if you try to tie it off horizontally, remember you're taking the horizontal product. That would give you a cosine times an e to the x. We want to tie it off when we get a sine. So we still need another term. So we'll take the next diagonal, which is going to be e to the negative x times cosine. Then we go across and pick up the next sign, which is plus. And notice here, if you tie it off with the horizontal product, you get back to a sine of x e to the negative x, which is the two factors we started with. So we do want to tie it off right there. And remember, to tie it off, the process, you take the sine of the next term, which I already did, you tie it off with an integral. Now, it does end up being minus sine of x e to the negative x, or let me do it like this. Let me just call it minus the integral e to the negative x sine of x dx. Now, what do we do from there? Well, here's what we realize, that the integral that we started with is on both sides of my equation now. I have one over here and I have one on the right-hand side, so I can combine like terms. In this case, I can combine like integrals. I could bring this negative integral term across to the other side, and I can combine it with that one. So the integral of that plus the integral of that will make 2 the integral of that. And what am I left with on the other side? I'm left with negative e to the negative x sine of x. I'm running out of room here. Okay, and then minus e to the negative x cosine of x. And then technically, I guess there's a plus c. But I haven't finished yet. because I was trying to find the original integral, and right now it's solved for twice that. So if you remember, we had that one problem back in the day. To solve for the original integral, I'll just multiply everything through by 1/2. And I end up with the original integral that I was interested in finding the antiderivative of to equal negative 1/2 e to the negative x sine of x minus 1/2 e to the negative x cosine of x. And now I can evaluate it from 0 to infinity. And we'll do this one MC style. All right, so let's see what happens. When I plug in the top, I plug in infinity. Well, e to the negative x is in both terms. What is e to the negative infinity approach? 0. So I'm going to have a 0 times sine of infinity is technically d and e. But think of sine of infinity as just being some number between 1 and negative 1. Some number between 1 and negative 1. So it's going to exist. The y values will, even though the limit doesn't. So what is 0 times any finite number between negative 1 and 1? It should be 0. Yeah. So you're going to get a 0 on the first term. Same argument over here. You're going to have a 0 times any number between negative 1 and 1. So you're going to get a 0 there. So that's plugging in the top. Minus plugging in the bottom. Well, now we have to be a little bit careful. That's going to be negative 1/2. E to the 0 is 1. Sine of 0 is 0. Minus plugging in the second one, you get 1/2. E to the 0 is 1. Cosine of 0 is also 1. Now here's where you really have to be careful because we're subtracting. Plug in the top, minus plug in the bottom. But when I evaluate now, I have two terms that are minus. So there we go. And if I simplify that, what does that come out to be? All of that? 1/2? Yeah. It comes out to be 1/2. So a little bit of interesting math there. But if you're very diligent and you do it right the first time, it'll work. So this one is, again, a little bit beyond the scope of what you'll see on the AP exam. You're not going to have one where both of them are repeaters and you have to tie it off. I'm just kind of reviewing some of the cool integration techniques because now it's really all on the table again because we have a new interval of integration. So speaking of, if we looked at this one, we spot the infinity, so it's really easily recognizable as an improper integral. The derivative at the bottom is 2x plus 4. There's no two terms in the top, so we have not a natural log rule. We can't split it up because we have three terms in the top. Long division doesn't work, so what did we then say to do in the bottom? We attempt to factor it. And if it factors into a binomial squared, great. Then it'll be a power rule. We'll bring to the top. If it doesn't factor at all, we can complete the square, and it turns into an inverse trig. I don't know if you remember that. Or if it factors into the product of two non-repeating linear factors, which I think this one does, then we can integrate it by partial fraction decomposition, Heaviside method, yeah. So I brought the 2 out front, but I don't know if you remember, I said maybe it's best when you do that just to leave the 2 up there. It's up to you. So I'll go ahead and create my 2 terms down below. And I'll leave the 2 in the top. So a negative 1 makes this 0. If I plug in a negative 1, I get 2 over 2, which is 1. See? So there's another good piece of evidence why you might want to leave the 2 there. And then a negative 3 makes the top, or the second factor 0. Plug in a negative 3 and you get 2 over negative 2, which is negative 1. And now you can evaluate both of them. So we'll do it MC style again. Here's where you want to be a little bit careful. There are always going to be natural log rules of integration when you have linear factors, but always check the derivative. If it were like a 2x plus 1, you'd generate an unwanted 2 and you'd have a correction of 1/2. If this were like 1 minus x, you'd be off by a negative and you'd have a correction of a negative 1. And that's real easy to overlook. But in this case, the derivative of both linear functions is just 1. So there's no correction to make. So it's just the natural log of x plus 1 minus the natural log of x plus 3. And now we have to evaluate it from 0 to infinity. Well, here's the problem now. If you try to evaluate it, you plug in infinity and you get the natural log of infinity, which is what? Infinity minus infinity. What's infinity minus infinity? It could be 2. It could be D and E. It's indeterminate. So that's not the most useful version. So I need to somehow get those 2 terms into one term. And the easiest way to get these 2 terms into a single term, is to condense the logs. So there's the natural log of the absolute value of x plus 1 over x plus 3. The 2 got absorbed when we split it up, right? I left the 2 up there, so -1 made it 0. I covered it up. So now I have a 2 over a -1 plus 3, which is a -2. Right? So 2 over 2. 2 over 2 is 1. So the 2 got absorbed in the decomposition. All right, so now if we're evaluating it, remember you can evaluate, and this is why the limit idea is best. You're going to evaluate the inside first. So forget about the log. What would be the limit as x goes to infinity of 1x to the first plus 1 over 1x to the first plus 3? It is infinity over infinity, so if you wanted to do L'Hopital's rule, it would be the derivative of that over the derivative of that, which is 1 over 1, which is 1. So in other words, you could just do the end behavior. Since we're going to infinity, it's 1x to the first over 1x to the first. When they have the same degree, it's leading coefficient over leading coefficient. So the inside part approaches 1, which means we have now the natural log of 1, which is 0. So when you plug in the infinity, it approaches 0. Minus, when you plug in the bottom, you get the natural log, bless you, of 1/3. And so your answer is negative natural log of 1/3. But this would be a perfect type of question for a non-calculator multiple choice. And I doubt that would be an answer choice. So what else could we do? You could bring the negative back up, remember, and say it's 1/3 to the negative first power. And of course, anything to the negative first power is the same as the reciprocal. So it's the same as the natural log of 3, which is just a little bit better looking answer. There's no negative and there's no fraction. So that one ended up converging, which you would probably anticipate that it would converge. Because notice that we're going out to the right, and if you kind of strip down the other part of the polynomial, it looks like it's very similar to a 1 over x squared. And we talked about the p-series yesterday. If we're going out to the right, a 1 over x squared would go to the x-axis fast enough, okay, as long as the exponent's bigger than 1. And all the other stuff is really insignificant in terms of the convergence of it. So this one should converge, and it does converge to the natural log of 3. Good stuff. So I don't know if that was really rapid fire, bless you, because each one took a good amount of time, but maybe we did them as efficiently and quickly as we could without making careless mistakes. All right, questions on example 7. Indeterminate forms. We're getting into infinity, which is always a lot more fun. Okay, so it says determine if the following converge. If they converge, find the value. This might be helpful, though. Just some facts right here, and which will transfer into the series. If you have the sum of 2 convergent things, then their sum must also converge. You can think of convergent as finite, right? Finite plus finite is finite, so convergent. Divergent plus divergent should be divergent, right? Infinite plus infinite, or negative infinity minus infinity. They go in the same direction. You got to be careful, though, if it's infinity minus infinity. So divergent minus divergent, you have to be a little bit more careful. Divergent plus convergent, well, that would be like infinite plus or minus finite. That's going to be infinity still. So whenever you have a divergent in there with a convergent, the whole thing diverges. And then, of course, the one I just told you about, divergent minus divergent, is indeterminate when the signs of the infinities are opposite. So how can that help us evaluate stuff like this? Well, we'll see. We spot an improper integral, pretty easy, and we're going from 1 to infinity. I need to be able to find the antiderivative. Now, let's start doing the following. Do you anticipate this to be convergent or divergent? Because your intuition can take you a long way. Why? You're right. the bottom is bigger. If the bottom were x cubed, it would actually be convergent, though. Yeah, you want to kind of strip away all the layers like we did in the last one what I mentioned. If you just took the leading terms in the top and bottom, it would be x to the first over x squared, which simplifies to 1 over x, right? And we know what about 1 over x? It diverges, right? That's the cutoff. And so having the plus 2 up there, you think it's going to help it go to the x-axis faster? No, having a 2 in the top only makes it go to the x-axis a little bit more slowly. So every function essentially is going to behave like the quotient, the simplified quotient of the leading terms. So this is going to behave a lot like a 1 over x. If you could spot that on a multiple choice question very quickly, you can get to divergent, and that might be an answer choice, diverges or divergent, or it might be infinity or negative infinity. This one would be infinity because 2 plus x and x squared are both positive for large values of x. If you didn't spot that, let's prove it. You would have to be able to find the integral, and this one would require you to be able to split it up. So if you integrate it, you're going to have 2 over x squared, which is really 2x to the negative second, plus x over x squared, which is 1 over x. So you can actually compute it. This one by the power rule is going to be x to the negative first, divided by negative 1 makes that a negative 2, and this becomes the natural log of the absolute value of x. And we'll do it MC style, 1 to infinity. So remember, negative 2x to the negative first, I'm going to rewrite that up here. It's really negative 2 over x. So when you plug in an infinity, you get, first of all, negative 2 over infinity, which approaches what? 0. Plus the natural log of infinity is what? Infinity. Yeah. Minus when you plug in the bottom, you get negative 2 plus the natural log of 1 is 0. So it ends up being infinity plus 2, which is cute. Infinity. Like little kids playing games, right? I know you are, but what am I? Infinity. Infinity plus 1. Infinity plus 2. Infinity plus infinity. Infinity times infinity. I'm leaving. Whatever. So there you go. It diverges. So a little bit of thinking on the front end can save a little bit of time on a multiple choice question. All right, let's look at this one. 1 over x, we know it diverge, right, by itself, that term. And then 3x over 1 plus 5x squared would grow similarly to an x over an x squared, which would again be a 1 over x, which would also diverge to infinity. So here we have an infinity minus an infinity. And because they both kind of come from the same type of infinity, both from a 1 over x, this one may be finite, actually. It's indeterminate for sure. Infinity minus infinity. So I guess we just better do what? When in doubt, work it out, compute it out, dance it out. Okay? I don't know. MC style? You okay with that? All right. So 1 over x becomes what? Antiderivative? ln, good. Absolute value of x. Minus. The next one. Interesting. There's your inside function, 1 plus 5x squared. What's its derivative? 10x. Do we have a 10x in the top? We have a 3x, so the 3 goes along for the ride, and now we're just off by a 10, so we'll have a correction of a 10. So with the 3 going for the ride and a correction of a 1/10, we end up with a 3/10 coefficient, and then the rule of integration is ln. So we get ln of 1 plus 5x squared. 1 plus 5x squared from 1 to infinity. Okay, so when we plug in the top, we're going to get infinity minus infinity, which doesn't work. It doesn't work. That's indeterminate form. So how are we going to rectify that? Can we condense this one as easily as we did the previous one? No, because my coefficients are different. Is there another way to condense it if the coefficients aren't the same?
I'm going to go with
Probably so. There's one surefire way to make the coefficients always a 1 or a negative 1. You could bring that up as an exponent, right? That would make this whole thing to the 3/10 power. It's worth the shot. So now I'll have the natural log minus the natural log. So that could be condensed the natural log of the positive term gets its argument in the numerator. And then the negative term gets the argument in the denominator, which would be this whole thing now to the 3/10 power. And then I can evaluate that from 1 to infinity. So I put it at least in quotient form. And now, because it's in quotient form, I can focus on the argument and not worry about the log right away when I evaluate it as x goes to infinity. Well, since we're going to infinity, here's where knowing the hierarchy of end behavior would be really, really helpful, because now we have infinity over infinity, and we could use L'Hopital's rule, but the top, remember, is an x to the first, and the bottom is effectively a what? An x squared to the 3/10, which is what? X to the 6/10 or 3/5, right? So the exponent in the top is a 1. The exponent at the bottom is a 3/5, which is less than 1. So which one grows faster for huge values of x, top or bottom? The top, because it has a larger effective degree. And any time the numerator grows faster than the bottom, the answer is going to be some type of infinity. In this case, it's going to be positive infinity. So you're ending up with the natural log of infinity minus the natural log of, is it infinity? No. It's 1 over 6 to the 3/10, which is a finite number, right? Well, what's the natural log of infinity? Infinity. And what's infinity minus a finite number? Infinity. Yes. So this one actually now, we know for a fact, does what? Diverges.
I just had a breakthrough. Like,
You did?
infinite is
The absolute value of positive infinity is infinity?
infinite.
No?
Infinite has finite in it. Like
It does. Infinite. Yeah, finite and infinite. Maybe unfinite you would have caught on sooner. Finite and or not finite or unfinite. Yeah. Indescribable means not describable. So infinite means not finite. Yeah.
Didn't click until you wrote it. Next one is
Hey.
infinity.
Any kind of aha moment is good. Yeah. Regardless of when it comes.
It got me.
That's good. That's good. So this one's kind of interesting because it's really the same type of infinity, 1 over x and an effective 1 over x. But yet when you cancel them out, it doesn't truly cancel to give you 0. It's because the other things in this other term, the 3 and the 5 and the 1, they're affecting that one in such a way that it doesn't just cancel out. So pretty cool. Pretty cool. We're going to finish there with example 8. This is a kind of a large section, so tomorrow we'll just kind of get back at it. We'll look at maybe one example where both intervals are infinity. What would be the notation we'd expect to write for that? And then we'll look at ones that are indeterminate but a little bit harder to recognize because they don't have infinity in their interval of integration. All right, any questions for today? All right, you got 45 seconds to pack up and shuffle towards the door.